Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we're going to learn a very different type of mathematics, and it is called statistics and probability. And as you can see, it is marked as a 4-star lesson. There's no hiding it. This is a bit of a challenging course. This is an entire course in itself, and I believe next year as 11th graders, inshallah, you'll be taking it either with Mr. Sam or Mr. Arnie as an elective that's required. But for now, you're going to be introduced, inshallah, to stats and probability. I'm going to teach you guys counting methods and things of that sort. This is actually my major, stats. I'm not a pure mathematician. I'm actually an applied mathematician. So statistics, which is a much harder level of mathematics than most people know, is something that I specialize in. So one thing that I just want to talk to you about really quickly is the relevance of this topic. So here's a sample ACT report for a student, not necessarily a Salam School student, but basically you guys are coming to the end of all of the things that you need to know for the ACT. You know number and quantity, you know algebra, you know functions, you know geometry, you know how to integrate essential skills, you know how to model. We've done so much modeling. Modeling is basically word problems, and you know how to do many of them now. So what really is left in the balance is something called statistics and probability. All right. So inshallah, it just doesn't mean that you don't know anything about it. Much of it you will know, but I'm going to be filling you in for especially that probability end that really confuses students, it confuses adults, it confuses teachers, everybody, right? So inshallah, listen carefully to this lesson and I will be able to benefit you. Just a little word of advice, the problems for the ACT, they do run a number of pages because it's been a while since we had encountered something like that, but they run for 4 pages. And so I have split this lesson across 2 different components just to make this manageable, especially considering how by the time you start this lesson, it's probably going to be the month of Ramadan. All right? So let's go ahead and get started. The first thing that I'm going to teach you is called counting. All right? And you might be thinking to yourself, wait a minute, I thought I already knew how to count. So it's a slightly different way of counting. But basically, there's 2 ways that we tend to count. One of the ways is called a permutation. All right, so let me explain to you what a permutation is. For 5 people. All right, so let's suppose there was 5 people, and let's call these 5 people A, B, C, D, and E. Now, these 5 people are running for office. All right, and the most number of people that we can have is 2 people who are winners, all right, if you want to call them winners. So we can only choose 2 winners out of these 5 people. Furthermore, the first person to get selected is going to become the president, and the second person to get selected is going to become the vice president. Okay, so let's take a look at what we mean by order matters, right? What does it mean when order matters? Well, let's get started. Let's just give out a few samples. Let's suppose that person A gets selected first and person B gets selected later. So there you go, you got your 2 winners. What if B was to get selected first and A were to get selected later? So although one permutation is AB and one is BA, they make a whole lot of difference. It does matter who came first and who came second. So if you want, you can even pause this video and say, well, what other combinations could we have had? We could have A and C, and then we could have had C and A, right? We could have had A and D, and then we could have D and A. So as you can see, this list would be quite lengthy. This list would go quite long, and in the end, you would have a certain number of permutations. So this technique of counting, what we're doing here, we're looking at all the permutations that we could have. That would take quite a while. So what we have is a very useful method of getting this problem done. We would say, look, I have 5 people and I am trying to get a permutations of 2 people. So when you do that, you may just put into the formula where the n and the r belong. So 5 prime, or 5 factorial, 5 minus 2 factorial. And so that would give you 5 times 4 times 3 times 2 times 1. And in the denominator, you would have 3 factorial, because 5 factorial over 3 factorial. So that would give you 3 times 2 times 1. And the conclusion that you would make is the 3 and the 3 cross off, the 2 and the 2 cross off, the 1 and the 1 cross off. In the end, you are going to have 20 such permutations. There's going to be 20 such permutations or possibilities of this actually occurring. So this is the first technique of counting, and what makes it so unique is the order in which people are selected. It does matter. Now, let's take the same exact idea and let's go over to something which is called a combination, where we say the order doesn't matter, but that's not very clear for students all the time as to what do you mean the order doesn't matter. So let's take the same exact number of people, same scenario. You have 5 people, okay, and you're choosing 2 winners. Now, in this case, what we say is, listen, it doesn't matter who comes first and who comes second. You're both going to be selected equally. You have equal rights to this seat that we're offering. And let's suppose that it's just a representative seat, right? Like a class representative or something like that. You're both going to be reps. So now let's think about those combinations that you could possibly have. You could have person A becomes a rep, and then person B becomes a rep. Remember that there are 5 people in this mix. There's A, B, C, D, and E. There's 5 people here. But we're saying that they're both going to become reps. So now automatically, see, nobody says order doesn't matter. It's the scenario you're in. You're in a scenario where both of them are going to be representative. So then it doesn't matter who gets selected first and who gets selected later. So you could have B and A, but then somebody will argue, wait a minute, A and B is the same thing as B and A, because now the order in which you selected them doesn't matter based on the position that we're giving. And so this is how this is different than a permutation. You don't use that second combination. You only use one of them, otherwise you'd be double counting. So let me give you another scenario. A and C is going to be a combination. Now, what can you not say? You can't say C and A. That is not going to be counted anymore. So like this, you can again pause the video, right? It takes a lot of thinking to do these problems, but pause the video and see if you can enumerate all the number of ways that you could have 2 winners show up. Remember, I keep showing you A and people, but remember, you could go to D and E, and D and E is a combination. And then C and E could be a combination, like that. See how far you could actually go. Well, as you realize that it's easy to miss something. So what we do is we use this technique called the combination method. And the combination says 5 combination 2, or 5CR. And 5CR basically says that you start off with 5 factorial in the top. You multiply by 2 factorial and 5 minus 2 factorial. So if you give it some thought, that's essentially 5 factorial over, Bismillah, 2 factorial times 3 factorial. And if you simplify that a little bit, that's 5 times 4 times 3 factorial. And in the bottom, you have 2 times 1 times 3 factorial. So the 3 factorials, just a neat little trick, you can cross those off. The 2 and the 4 can be crossed off into 1 and 2. And so we come to the conclusion that you have only 10 unique combinations that you could have. Notice that it's still 5 people, and it's still you choosing 2 out of those 5 people. But all of a sudden, when the order does not matter, you just think of it, it's common sense. You're automatically always going to have lesser as far as the combinations are concerned because the order doesn't matter anymore. So saying AB is the same thing as saying BA, so you can't double count those. Whereas in that previous scenario, saying AB was one unique thing and then saying BA was another unique thing. So that's the first thing that we talk about as far as counting is concerned, is what's a permutation and what is a combination. So I will show you several examples in this lecture as far as which one is which. But for now, the next thing that we're going to do is we're going to talk about a Venn diagram. Now, it's possible that you've never seen a Venn diagram, and it's possible that you have, but maybe you've never seen it in the context that I'm about to teach it to you. Okay, so first, let's just kind of get an idea to make sure people do understand Venn diagrams. Basically, this is very similar to what you might have in your English class. Let's suppose that you had two groups, right? Let's suppose here. Let me just copy this really quickly. It's hard to talk and do something like this. So let's suppose that you had two groups, all right? And one of the groups likes. Let's suppose that they like Coke, all right? They like Coca-Cola. And let's suppose that another group likes Pepsi, all right? And so if there are, let's suppose 50 students, or let's make it 40 students in this class. Let's suppose that there's 40 students altogether. Then what we do is we actually make another boundary around the shape over here, and we'll talk about what that boundary represents in just a little bit. So this right here is called a sample space. All right, this is called our sample space. This contains all the possibilities of things that could happen. Everything that could possibly happen is contained within this rectangle. Now, let's suppose that there are 15 people out of these 40 people who enjoy Coca-Cola. So there's 15 students or 15 people here. Let's suppose that there are 20 people who enjoy Pepsi. Now, what does it mean if I put the number 2 on the inside? What does that stand for? Think about it. What am I trying to say there, right? And so what I'm really trying to say is the following. I'm saying that basically here is the circle, right? Here is that circle of people who like Coke, right? And here is a separate circle of people who like Pepsi. Right? Now you'll notice in my shading that there's a bit of an overlap. So the question is, what does that overlap represents, right? And if you are thinking to yourself that overlap represents the number of people who like both Coke and Pepsi, then you have gotten the point across, right? You've understood the point is how many people like Coke only? There are 15 such people. How many people like Pepsi only? And only is a very important word here. There's 20 such people. How many people like both Coke and Pepsi? There's 2 such people. Now, I think that, obviously this example is, it's a bit exaggerated. Most people are often inside of that circle, but inside of that overlap. But there you go. That's what that 2 represents. Now, if you count up, there's 15 plus 2, that's 17. And 17 plus 20, that's 37. So somebody might say, wait a minute, there was 40 people in the class. Where did the other 3 go? Right? Where did the other 3 go? And so first off, let's write those other 3. Those other 3, we're going to write them in a corner somewhere, okay? They're neither enjoying Coke, nor are they enjoying Pepsi, nor are they definitely in the middle of the two, right? And so when we want to describe that situation, we say that they don't like either Coke or Pepsi, and there's 3 such people in this classroom who are like that. So you want to absorb this idea and realize that all of this right here was not necessary because the Venn diagram was giving you that information altogether. So oftentimes you'll get a situation on an ACT or in the questions that you'll be doing, and the questions will say that there are 17 people who like Coke, and there are 22 people who like Pepsi, right? They'll say something like that, and then they'll say that there's 2 people who like both. And you'll be thinking, wait a minute, you just changed the numbers. I did not. See, before I had used the word only. When you say only, you're referring to a specific area. When I say only for Pepsi, that's only the blue area that's not overlapping. That's the one over here. That's that part of of that entire circle. It's not that overlapping piece. And when we say that Coke only, then that is only representing the part of the circle once again that's not including that overlap. But when the book says that 17 like Coke and the 22 like Pepsi, they're not differentiating. You see that? They're not differentiating. Is this the people who are only, or is this the people all together? And then in that case, what they're saying is there's 17 people in the Coke circle and there's 22 people in the Pepsi circle. But then you would argue and say, wait a minute, isn't there 2 that are being double counted? Because you counted them in Coke and then you counted them again in Pepsi. So what you'll find yourself doing in counting methods is you'll take these 2 numbers, you'll add them up, and this has confused students a lot in the past, right? You'll add them up and you'll subtract 2 from it. And the reason why you subtract 2 once again is because when you counted 17, you counted those 2 in the middle. But then when you counted 22, you again counted those 2 in the middle. So you're getting rid of that double count by saying something like this. And when you do that, right, what are you really looking at? You're looking at the number 37. And what does 37 represent? 37, once again, it represents, whoops, sorry, not 37, right, 3 and 9, yeah, 37. 37, it represents altogether those 3 sets of people. All right, that's what that really stands for. And then the 2 that were both, look at where they showed up. I subtracted them out once. So all that's left over after you get 37 is you're like, where's the people that, because if there's supposed to be 40, and so then you would say, well, 40 minus 37 is equal to 3, and that's where that neither comes in. And so we say there's 3 people who neither like Coke nor do they like Pepsi. All right. So that was one example for you that's not necessarily in the book. Now, you need to know a little bit of terminology, and so we're just going to talk about this really quickly. Number 1, when you want to say A or B, all right, when you want to say A or B, then what we use in statistics and probability is we use A union B. So we make a larger uppercase U and we say A union B. Now, when we want to say A and B, when we want to say A and B, then we say A intersection B. And one way to remember that intersection part is if you think of I, N, T, R, S, E, C, T, I, O, N. So then that kind of that piece right there, it sort of gives it away, that intersection. And so now let me depict for you what that means. What is a union? What is an intersection? And I want to do it on the simpler diagram before I go to a 3-circle Venn diagram, especially for the people who've never seen something like this before. This is probably quite a lot. So let's take the same exact diagram that we had earlier and we'll just make arrows to it and we'll talk about that. So here is the first piece. All right, here's the first piece. We will call that, okay, just that piece right there where nothing else is present, we will call that, let's suppose, C, and C stands for Coke. Then we'll call this circle right here where nothing else is present except that, we'll call it P. All right, so one is called C and another is called P. So in terms of statistics and probability, that middle section that you're looking at, that right there is called C and P. So you say C intersection P because it physically it looks like the intersection of the two, but it's also telling you that that's both of them. That's the people who like Coke and that's the people who like Pepsi. Now, what about C or P? C or P, right? Where is that exactly? If you're talking about C or P, you're saying that they like Coke or they like Pepsi, right? They like either they like Coke or they like Pepsi. In that situation, that would be the entire region altogether. Now, the best way I can explain that to you is I'll just mark around that entire diagram and I'll say everything that is within these two circles is represented by C or P. So that's the most generalized way to do it. And so C is equal to 15, P is equal to 20, C and P, which is very restrictive, is only 2, whereas C or P, meaning you could like Coke or you could like Pepsi, that's actually 37. All right, so you're seeing how all of that comes about. And so all that you're left over with, as far as hasn't been counted yet, is the piece that's outside, right? The piece that's outside that hasn't been included in either one of those circles. Now, might be a little bit beyond the level of the course, but you're probably interested to know, what exactly would that be? Basically, what you could say that it's C or P and then put a line above it. And if you put a line above it, that line represents it that it's neither one of those situations. So it's basically 40 minus the 3 minus the 37, which gives you the 3, right? So we're talking about in that space there's people who neither like Coke nor do they like Pepsi, and that's the notation that we use for it. So now having said that, basically you're looking at a Venn diagram here, which has three such, and it's not in the book, okay? The book only gives a very general idea of how this works. So, that's one of the limitations that you have. Now, take a look at it. I don't have to run you through everything, but basically you can notice that there's this middle overlap between all three of the circles. And basically, in the middle of those three is A intersection B intersection C. And then in each one of these ends over here, that this component, right, this component right here, it's basically the intersection of the B circle and the C circle, but it does not include anything of the A circle like that. And so you can continue to look at this. Now, one of the things that I've taught in physics as far as optics, and I feel like I could bring some of that to the classroom right now, is if you guys take a look at these colors right here, these are what we call the primary colors. And basically you've got the red, you've got the green, and you've got the blue, right? And then when you take blue and you take green and you put them together, you get a different color. I recall this is like cyan or something like that, right? And when you take red and you take green, you get yellow. And when you take red and you take blue, you get magenta, right? So what's left over in the middle, right? Actually, I shouldn't say what's left over, but when you take these three colors, when they combine together, that's actually the white light that we see, right? That's actually the white light. When that's reflected, that's what we're seeing, all that white light right there, okay? So now having said that, basically you're going to have something in the homework, which if you understand this, it's not going to take you anywhere as long as it's taking me to explain it to you, right? But it'll say how many are in set A, how many are in set A or B, like that, right? So let's just put some numbers into the mix over here just to kind of have some food for thought. And so I've gone ahead and I've put some numbers in the spaces just so we can talk about them. All right. So here goes. Bismillah. Number 15 says, how many are in set A? Right. So set A, would be the entire circle of A. Please understand that. So that would be 10 plus 2 plus 5 plus 3. And 10 plus 2 gives us 12, plus 5 gives us 17, plus 3 gives us 20. So in this situation, there are 20 in set A. Now, number 16 says how many are in set B. So let's go ahead and take a look at set B here. And if you take a look at set B, in set B, you have 12 plus 2, that's 14. 14 plus 5 is 19, and 19 plus 4 is 23. So there are 23 in set B, like this. Now, number 17, it says how many are in set A or set B. So this is where it starts to get a little bit tricky. So look, we already said that there was 20 in set A, didn't we? Right? That was number 15. So realize if you said that there's 23 in set B, you just double counted these 7 in the middle. So what you really need to do when you're asked that question is you're supposed to take what you had in set A, add it to what you got in set B, but then you got to subtract out the 7 that are being double counted in this situation. And so how many are in set A or set B? Really, it's 20 plus 23, which is going to give you 43, and then 43 minus 7 is going to give you 36. So there's actually 36 that are in set A or B. And if you want to know one simple way to count this is why the numbers exist there. 12 plus 4 is 16. 16 plus 2 is 18. 18 plus 5 is 23. 23 plus 3 is 26, and 26 plus 10 is 36. So I manually went to every single space and I counted it, and that way it refrains from double counting at all. Now, number 18, it says how many are in A and B, right? So A and B would be this middle intersection on the bottom, and so that would be 2. There's 2 that are both in A and in B. Okay, now let's take a look at number 19. It says how many are in A but not C. So this is where it starts to get a little bit tricky. So I want you to think about everything that's inside of A. Okay, so let's go ahead and highlight, just kind of circling around this. Here is everything that is in set A. Now once again, how many were in set A? According to number 15, there was 20 in set A. But what they're telling you is now what you got to do is you need to exclude everything that's already in A from everything in A. You have to take out everything that's in C within A. So in other words, all of this circle right here, all of this is going to get X'd out. Why? Because it's inside of C, and we can't have that, right? So what we do is when we get rid of something like that, when they say how many are in A but not C, well, there are 12 that are going to be inside of A, but they're not inside of C. Now, one thing that tends to confuse students is like, wait a minute, but these two are in B as well. Yet don't make up new conditions. As long as the logic is sound, you're good to go. You made sure that these are in A, but they're not at the same time in C. Okay? All right, let's try the next one. Number 20. It says how many are not in A? Meaning now you need to count everybody that's not inside of A, right? So here's A, right? Get rid of everybody from A, right? Get rid of everybody from A. So they can't be in A. That one's crossed off. What's left over? 7 plus 4 plus 12. That's only people who are not in A. And so 16 plus 7 is 23. And so you end up with the answer 23 are not in A. All right, let's continue, inshallah. I believe I had some numbers up here and I lost them. Give me 1 second. I apologize for that. I had accidentally in erasing, I had gotten rid of the 5 and the 3, but they're right back, I believe, where they were supposed to be. Number 21, it says how many are in A and B and C? I would say that was probably the easiest question for all of us. We're like, that's easy, that's 5, right? That's the one in the middle right there, so that takes care of that. Now, how many are in A or B or C. So this is the one that's the most fun if you think about it. That's basically saying that you can be in this circle or that circle or that circle. And then you would say, wait, so you could be anywhere that you want. Basically, that's what we're saying, right? And there is no other outer space here where you got numbers. So 10 plus 2 is 12, plus 12 is 24, plus 4 is 28, plus 5 is 33, 36, and altogether you have 43. So there you go, that ends this exercise. So that's the first thing that you need to learn in counting. And I wish I could say that that's the hardest thing, but that might arguably be the easiest thing about counting right there, all right? Now, let's go to a different thing to do. And it says a woman has 5 blouses and 8 skirts. How many different outfits can she wear? So in middle school, what you may have had, your teachers may have said, look, let's suppose that you have 5 possibilities of blouses, okay? And then each one of these possibilities has 8 possibilities of skirts. And so each one of these, I'm just drawing one of them because literally that would be just so many possibilities. Let me draw a few more here. So I got 1, 2, 3, 4, 5, 6, 7, and 8, right? So each one of these has 8 possibilities of skirts after this woman has chosen her blouse, right? And so what we're really saying is, well, if A was to be chosen, then she has 8 possibilities. B was to be chosen, then she has another 8 possibilities. And so really what we're saying is to every one of these possibilities, there is 8 more to go. And so altogether, when they say how many different outfits could she wear, she can wear 40 outfits. And what you just did here is called a very important piece of counting. It's called the counting principle. All right, it's called the counting principle. And the counting principle essentially says that whenever you have a situation where you have to choose N things and then you have to choose P things after that, well, and if you were to choose R things after that, then the generic format of it is N times P times R, and you pick any other letters, but basically the number of choices or categories of choices that you have, then accordingly you have to multiply those as well. All right, so that's number 24. Number 26, it says how many 5-digit numbers can be formed using the digits 0 through 9 if the first digit cannot be 0 or 1. Now, first off, there are 5 digits in this number. And the safest way to do this question, right? The safest way to do this question is say, okay, let's make 5 spots. All right, so I alluded to this idea back when I started sequences, and here is that idea again, right? So here is 5 spots. Now, it says you have the option of 0 through 9, but the first digit cannot be 0 or 1. So what does that tell you? For that first digit, how many choices do you really have? From 0 through 9, that's actually 10 choices. But if you can't have a 0 or 1 in the first digit, then that's 8 choices that you have. But then for the rest of the digits, well, it says you can repeat the same digit if you needed. So for instance, if you had the number 4 in this, it's okay to have another 4 here and another 4 here. So in other words, the number of possibilities is not going to diminish after that. So what you essentially have is you have 10 choices for the next spot, 10 more choices for the next spot, and like this, you've gotten a certain number of choices. Now, once again, if you want to figure out how many such numbers can you make, you have to multiply all of these, and you end up with a pretty large number because 10 times 10 is 100, times 10 is 800, times 10 is 8,000, and then 8,000 times 8, I believe, is going to give you 64,000. So you can actually make 64,000 numbers that are 5 digits long based upon what they just allowed us. I just want to make up another problem while we're here because these are some things that just confuse people like a lot. And so what if it said that repeating digits is not allowed? If repeating was not allowed, right? And just to make it a little bit more simple, let's just suppose that you can pick 0 or 1 for that first spot. All right, so let's make those same 5 spots again, but this time let's just assume that you can have 10 choices. You can have any of the digits in that first spot, just to drive the point home here. Okay? All right, now let's get to thinking. By the time you get to the second spot, remember, if you already picked the number 4 here, you can't pick the number 4 here. In other words, you only have 9 choices for the next spot. And then using that same logic, because repeats are not allowed, your number of choices are diminishing as you go further and further. And so altogether, you get a much smaller number than you got earlier. And pretend you're in a room, okay? Pretend you're in a room and there is a bunch of other people in that room, and they put out a bowl of candy, and they say that you can pick 5 pieces of candy from this bowl, right? And you go there and you start picking out pieces of candy, and think about it, in real life, which one of these situations is more realistic? Is is it more possible that you are picking up candy and you still have the same number of chances of getting that same candy all over again? Or is it more possible that as you pick up more candy, there is less and less chances of other people getting that same candy, right? So this is the more realistic situation. That one, not as much. Okay, that one not as much. But more on that, inshallah, um, as we continue. All right, in this example, it says in a student survey, 200 indicated that they would attend summer session 1, and 150 indicated summer session 2. So let's just suppose that we've got 2 bubbles here, right? So we're talking about people who want to attend session 1, and session 1, there's people who are 200 in number who want to be in that session. And then in session 2, let's keep these bubbles apart for now, right? There's 150. But then this image is not, 150, right? This is not completely valid yet, because look at what it says later. It says if 75 students plan to attend both summer session, now we've got an issue. Basically what they're saying is the following, right? They're saying that you have to make these 2 diagrams come together like this over here. All right, you still got 1 and 2, but this time, here's what's happening. There is 75 students who were counted in that 200, and those same 75 students were counted in the 150. What am I trying to say to you here? Now when you write down the numbers, you got to make sure that you take 75 away from 200 and you write down 125. And then you take 75 away from 150 and you write down 75, because that's what 150 minus 75 is. So if you're wondering, wait a minute, you just changed the problem. The problem when they began it was not a complete problem. They didn't tell us the whole situation. Now they're telling us that here is the real situation. You've got 75 students that plan to attend both of those summer sessions. So in truth, there are people who are going to be in session 1, that's 200, and in session 2, that's 150. But then we were missing that key piece of information that there's 75 who are going to attend both of them. So we had to include that overlap. Now, it continues, and it says 275 indicated that they would attend neither session. Now, here is the thing. They don't want to go. This is why I started with the example that I did in the beginning, sorry. There's 275 people who don't want to be in either one of these sessions. Where do we put them? They are still part of this survey, but they just don't want to be in either one of those sessions. So we put those 275 outside of those 2 bubbles, right? And we're not going to give them their own bubble. We're just going to say they're not within that bubble right there. So you're not going to find those 275 people sitting in either one of those rooms, right? You're going to find 75 people who sat in room 1 and also are going to sit in room 2. So when the question says, how many students participated in the survey? Well, in this scenario, here's 275 who participated in the survey, then there's the 125, and then there's the 75, and there's another 75. And so altogether, that's going to give you the total number of people who participated in the survey. Please realize, if you planned on doing this by ignoring those 75 students, because this is what, when I first learned this topic in like 6th grade, I'm like, I don't understand the overlap thing, right? So it's quite possible that you're still struggling with that idea. Look, if you had said 200 plus 150, that would have given you 350. And then if you had added 275 to that, this is important, so let's actually do the math here. 350 plus 275, that's going to give you 625. Now, if you did the same math on the bottom as I was explaining to you, 275 add 125 is going to give you 400. And 400 add 75 is 475. And add 75 is going to give you 550. What's the discrepancy? Look at the discrepancy. Look, there's 625 here. There's 550 here. How many more are we counting in this group? We're counting exactly 75 more than that group. And so that's what I'm trying to explain to you, is the double counting would occur if you didn't use the techniques that I'm showing to you. An Venn diagram is just a really nice way to kind of organize your thoughts onto paper. Now, we're going to try one last one that is quite challenging. This one, it took me some time to wrap my mind around. So I just want to talk about this one with you guys. Now, for this one, for this one, I would recommend that you pause the video and you try to diagram this by yourself. But here's the hints that I'll give to you. It's going to consist of two such of these circles, right, that I'm showing to you. And it's going to consist of that rectangular space that I've given to you. All right, so as I read this, try to see if you can diagram. This is truly a test of intellect to get through these, honestly. It's not your basic algebra anymore, all right? So let's go ahead and read this one at a time, and inshallah, I'll try to explain this to you as best as possible. So it says human blood is classified as either Rh plus or Rh minus. Now, they already talked to us. Let me use a different highlighter here. So they already talked to us as you can have Rh plus or you can have Rh minus. So we're keeping track here. All right, we're keeping track here. Rh plus, Rh minus. Now, it says that that's one of the classifications of blood. It says blood is also classified by type. So not only can you classify it by Rh, you can also classify it by type. And so the types they're talking about are the following. It says you can have type A. All right, so we're just first listing everything that could happen. Type A, if it contains an A antigen but not a B antigen. Then you can have it type B. All right, so type B is our fourth category. If it contains a B antigen but not an A antigen. Then it says the third type is AB if it contains both A and B antigens. So now we have a type that's called AB. All right. And finally, it says O if it contains neither antigen. So there is type O. All right, there's type O. So let's try to work with the A, the B, and the AB first. All right, so I'm giving you that hint. You can pause the video and see if you can do this by yourself. So what I'll do is I'll say, okay, how about we take one of these circles. All right, let's place it in the middle right here. And let's take the other circle, because there's clearly an overlap between the two. All right, there's clearly an overlap between the two. So there you go. I've got both of my circles. Just geometrically, I've tried to do my best to put them in those particular spots. So now let's give it some thought. All right. We, in the end, want to figure out how many different kinds of bloods can you possibly have based on all the stuff that they just said to us, right? So because they told us that human blood is classified as either Rh plus or Rh minus. Okay, so that was the first classification that we had. So I will take a line that goes straight down the middle like this. All right, and you'll see eventually why I chose to do that. But I'll take a line that goes straight down the middle and I'll say, look, you can have all of these different kinds of situations and types and still be RH plus, or you can have all these situations and types and still be RH minus. So that's me classifying human blood into two categories. Then after that, what I can say is the following. I can put inside of one of these circles type A, and I can put inside of one of the other circles type B. And then what I can say is the middle of the two can be my type AB. Because they did say that AB was kind of the one that could contain both A and B antigens, right? So it could have A antigens and it could have B antigens. So there you go. It kind of takes the intersection of those two right there. And finally, the last thing that they had said is, O, it contains neither antigen. So where would O belong? O would be outside of the set, right? So I'm going to put O over here. Now, let's go ahead and understand one thing. What we were trying to imply is you can be part of this classification, right? You can be this top part of this classification, and you can be any four of these things. Think about it, all right? Here is number 1, here is number 2, here is number 3, here is number 4. So that's 4 types already. Then we can repeat that process and we can say that you could be inside of this classification, the RH minus classification, and you could still be those same 4 things. So A, B, B, and O. So altogether, right, altogether you've got 4 more classifications. So I know that that was a very challenging way of organizing it. And it takes a while to get used to it, but there are actually 8 kinds of blood classifications, different kinds of bloods that you can have based on the information that they gave us. The next question that we're going to do is a lot easier. It says that the following data represent the marital status of females 18 years old and older in 2007. So if you were 18 years or older, you were counted in this right over here, this data, right? Now it says determine the number of females 18 years old and older who are widowed or divorced. All right, so just counting. This is a very basic example. So if you look at the number of people who are widowed and the number of people who are divorced, all you got to do is just go ahead and take those numbers, 11,105, and add it to 12,932, and that'll give you the number that are widowed or they're divorced. Now, the next one says determine the number of females 18 years old and older who are married, widowed, or divorced. So married, widowed, or divorced, it would basically take these same 2 sets of numbers and it would add to them additionally 63,971. And again, this is in thousands, by the way. Okay, so altogether, that gives you the answer to letter B. So that one was not so bad. I just wanted to include it in my examples here. Now the next thing that we're going to do is we're just going to practice with the permutation and the combination formulas that we began the lesson with. And basically the permutation formula, it says NPR is equal to n factorial divided by n minus r factorial. And NCR is equal to n factorial over r factorial n minus r factorial. And you can pause the video and try a few of these. I did try an example earlier, so I just want to take number 10 and try it with you for the first one. So number 10 says P8 comma 8, so that's 8P8. That's how you write it. Okay, so 8P8. And this book always uses the format N and then R. Okay, so 8P8 is going to be 8 factorial over 8 minus 8 factorial, which is going to give you 8 factorial over 0 factorial. And in a previous lesson, we talked about how 0 factorial is actually equal to 1. So really what you're doing is you're going to a calculator and you're typing in 8 factorial. And if you don't know how to do that in a calculator, recall that all you need to do is just basically press the number 8, and then you're supposed to go to math, and you're supposed to go to PRB, and then you're supposed to go to the factorial sign and press that in. But another reason I just want to kind of highlight this for you is because as you were looking at those steps, you may have noticed, and this was completely my intention to show this to you, by the way, is it did say NPR and NCR. I just want to show you how you can type the same thing in a calculator. So you can type in 8, go to math once again, or you can go to math, and then you can go to PRB, and go to NPR, right, and then go 8 again. And like that, it'll give you the same number, right? So you don't have to simplify it on paper necessarily. And then, I don't need to do all of these examples here. You get the idea. I just wanted to show you a mix of, the types of things that you could have over there. It's more important that we learn to, I think, apply them more than anything. So we're going to try number 24. Number 24 says, list all the ordered arrangements of 5 objects, A, B, C, D, and E, choosing 2 at a time without repetition, right? Without repetition. And so what we're going to do is essentially realize that what they're saying is we have 5 objects, all right? We have 5 objects, and we're choosing only 2 at a time, and you can't put A back after you pick A out, right? So they've got to be 2 different things essentially is what we're saying, right? So this is going to become 5 factorial over 5 minus 2 factorial. But remember, your calculator will do that whole thing for you. I just want you to take a look at the wording, right? Ordered, meaning the order does matter. And so they don't necessarily need to tell you do P5, 2. You should know that when they said ordered, that they're implying that you use the NPR formula. Okay, now I just want to show you an NCR as well. So it says list all the combinations of 6 objects. So we'll call them 1, 2, 3, 4, 5, 6, taken 3 at a time. And now they're not telling you that the order matters anymore, right? So for instance, let's just kind of get this out of the way just so you understand. If you say 1, 2, 3, because we're taking 3 at a time. If you say 1, 2, 3, then later on you get 3, 2, 1. This is what I started my lesson off with. You can't count the 3, 2, 1. Even if you got 2, 3, 1, you can't count the 2, 3, 1. Why is that? It's because the order doesn't matter. As long as you got a set with those 3 in it, it doesn't matter in which order they're arranged in. That doesn't matter to you. So if you get any more of these 1, 2, and 3 in that same set, you ignore that set. That's not included there. All right. Whereas earlier, because the order did matter and we had A, B, C, D, and E, and we're choosing 2 at a time, if you got A and E, and then later on you get E then A, the order does matter. So these are both counted as those possibilities. So when you're calculating this, it's included in those possibilities, whereas in NCR, it's not included in those possibilities. So those formulas save us a whole lot of headache. Even for me as a teacher, I get crossed up between this sometimes. So 6 minus 3 factorial, and so you have 6 factorial over 3 factorial times 3 factorial, and you're welcome to just use a calculator, inshallah, to solve that question right over there. All right, now it says how many 3-digit numbers can be formed using the digits 0 through 9, and repeated digits are allowed. So we've done something similar to this earlier. So we're talking about 3-digit numbers. All right, so 3 spaces like this, right? And you have to use the digits 0 through 9. There is no restrictions. Repeated digits are allowed, so you have 10 choices for the first one, 10 choices for the second one, and 10 choices for the third one. Altogether, that would be 10 times 10 times 10, and that'll give you the amount that you could actually have for each one of those. All right? All right, let's keep moving, inshallah. Number 38, it says, how many different 4-letter codes are there if only the letters A through F can be used and no letter can be used more than once? So now this gets a little bit more interesting, right? So you have to have 4-letter codes, right? So you can only have 4 letters. So 1, 2, 3, 4. Only 4-letter codes. And the only letters that are allowed are A, B, C, D, E, and F. So that's altogether 6 letters. So in other words, for that first letter in the code, you have 6 choices. For the next letter, you only have 5 choices. And if you ask why, it's because you can't use something more than once. Once you've used it, you can't use it again. So then the next one is going to become a 4, and the next one's going to become a 3. So in this situation, it becomes 6 times 5 times 4 times 3, and you definitely are going to have lesser things to choose out of because you're not repeating things. All right, here's another one. In how many ways can a committee of 3 professors be formed from a department having 8 professors? What I want you to ask yourself is, well, does the order really matter here? Right? Does it matter? Because they're all just going to be professors anyway, right? And so in truth, the order doesn't matter. Right? The order doesn't matter. To us, it's just 3 professors or 3 professors. It doesn't matter whether you chose one professor before you chose the other. As long as they 3 got chosen, that 3 has been chosen then. And so now you're really saying this is 8C3 because the order doesn't matter. So you're going to be taking 8 prime, or factorial, sorry, I keep saying prime because in a different course we use prime for this, and then 8 minus 3 prime, or factorial, and then you basically calculate that and it'll tell you how many ways this committee of 3 professors could be formed if there's 8 professors in the department, right? And as we're closing up with this lesson, one thing that we tell students often is we say N choose R, right? So there was 8 professors and we chose 3 of them. So 8 choose 3. It helps sometimes, but sometimes it doesn't really, how you look at it. The last question that we have today, it says, how many different license plate numbers can be made using 2 letters? All right, so there's 2 letters. All right, so let's clear this. This needs to be a letter. This right here needs to be a letter. All right. It says followed by 4 digits. So now we're talking about 4 digits. All right. So each one of these needs to be a digit. All right. So like that. Now you're probably wondering, can we repeat it or can we not? And that's the same thing that I'm wondering. So it says if the letters and the digits may be repeated. So now you ask yourself, how many letters are there in the alphabet? All right. So there's 26 choices for the first box, and as long as we can repeat, you can have 26 choices for the next box. But then how many digits do you have from 0 through 9? You have 10 digits, so 10, 10, 10, and 10. And all together, if you multiply each one of these all together, you're going to have a total number of combinations that you can have for that first piece right there. Okay, now letter B, it says the following. It says, okay, so this is letter A. Let's just label it. All right, now letter B. It says letters may be repeated, but digits may not be repeated. So you can have 26 times 26, but the digits cannot be repeated. In other words, you have 10 choices for the first digit, but then you have 9 for the next, 8 for the next, and then 7 for the last one. And so this is going to give us lesser possibilities. So lesser possibilities of number plates, but altogether we once again have figured out a way to work with letter B. Now, letter C says neither letters nor digits may be repeated. So in this case, you have 26 choices for the first set of letters, but then you have only 25 for the next. Then you have 10 choices for the set of numbers, But then you have 9, and then you have 8, and then you have 7. And again, you'll realize that this is even lesser options than we have from before. So good luck in doing the homework, and this is one of the reasons why I split up the lessons into 2 parts, because I know how challenging stats and probability is. Feel free to watch some of the videos that I posted. I'm not sure if the lesson notes are going to be too entirely useful. I have used them from courses that I've taught many years ago, inshallah. So good luck and Assalamu alaikum.